session. So I've got a talk by Helle Hansen from Delft University of Technology, Carlsberg perspective on multi-values and MDPs. Thank you.
Thanks, Neil. And thanks to the organizers for inviting me. It's a pleasure to be here. So yeah, I've been working on Markov decision processes together with my PhD student Frank Fals and Larry Moss from Indiana, who many of you know. And I'm basically presenting the paper we had at CMCS earlier this year. And well, this comes about as a general aim of applying algebraic / category theoretical techniques in order to reason about, well, Markov decision processes, but more generally, we also want to go to games. I'll say a little bit about that at the end. But this is as many of you know here, it's a program that was started by, Victor and Samson and Pierre and Jules, many other people who are here. So yeah, that's the general motivation. So first I should say, this is about Markov decision processes. So there are no games in the talk as such, and the MDP is also not open, but I hope it's still of some interest to the public here.
Do you have a suspicion about whether they can be open?
Well, the algebraic modeling doesn't really in itself capture compositionality, as you know, so I mean, you need to add something on top of that, right? But hopefully one can then derive behavior from composed systems using algebra. But yeah, I'm afraid I won't be saying anything about that. Okay, so here's an outline of my talk. First, I'll give some MDP preliminaries. Now, I don't know, maybe everyone here knows MDPs. I mean, I know there are people here who know MDPs much better than me, so I'm just wondering if who is fairly ignorant about MDPs? Let me put it that. Okay, good. So I'll go through this. And then in the two main contributions of our paper will be part 1 and 2, numbers 2 and 3. So it's about getting the long-term values of policies in basically using from a universal property, which is what we like. And for that, we introduce something called co-recursive algebras. And then I will use some of the things that we have set up in order to give a new proof of a well-known algorithm called policy iteration. And so we call it a proof of policy improvement using co-induction, essentially. Okay, so what are MDPs? Well, they have many applications. They are seen as state-based models of sequential decision-making under uncertainty. So this is a bit vague maybe, but I'll give you an example and a precise definition in a moment. But the intuition is that you have a system or an agent who chooses actions and collects some rewards. So the agent is operating in some kind of environment, and he hasn't got full control over what happens when he executes an action. So there's some probabilistic aspect to it there. And the object of the agent is to, find an optimal way to behave, so find an optimal plan or policy so that he will maximize his expected future rewards. And there are applications in many areas of engineering, so scheduling and planning problems in general, also in finance, and MDPs are also the formal models behind reinforcement learning, just to mention something. So and as I mentioned before, so there are no games as such in the talk, but the perspective one should have to link it to games is that MDPs are one-player stochastic games. So that's also the stepping stone to the work that we plan to do in the future. Okay, so here's a small example, just to give you some intuition if you never saw an MDP before. So we have here a 4-state MDP. So it models a situation where you have a startup company that needs to decide whether they will advertise, so invest money in advertisement, or they want to save money. So the 4 states they can be in is, they can be poor and unknown, or poor and famous, and so on. So you have here the rewards for being in the respective states indicated by a real value. And then the actions, basically, you have a probabilistic transition structure. So if you advertise in this state and the poor and unknown state, then there's a 50% chance that you will stay poor and unknown, and there's a 50% chance that you will become poor and famous, and so on. Okay, so more formally, we view MDPs as coalgebras. And maybe I should mention that there are many different variations of MDPs. So in general, the probabilistic transition structure and the rewards can depend on a time evolution, so on a time step. And you can also look at MDPs over continuous state spaces. But we're going to look at a simple case of discrete and time-independent MDPs. So time-independent meaning that the transitions and the reward structures are the same at every time step. So that means we can model them as a coalgebra of this type. So we have a finite set of states. We have a finite set of actions. We use here this notation for the monad of finite probability distributions with the Dirac distribution and the multiplication. So we have a transition function of this type. Sorry, this should be an S, of course. S should be an X, sorry. Yeah, and the rewards just map a state to some real value here. So as you see here, the rewards do not depend on the action. They only depend on the state here, but you could also consider a model where they do depend on the state. This is slightly simpler, but I mean, there's nothing essential lost in taking this view. Okay, so a policy, again, there are, because of the many different variations of MDPs, there are also there's a varying degrees of complexities in policies, and we are only going to consider what is called stationary policies. So the policy is also the same at every time step, which also necessarily means that it is memoryless. And we will also only consider deterministic policies, so not mixed strategies or mixed policies, but policies that just assign a single action at every state. So there are maps from states to actions. Okay, oops, did I? Yeah. Okay, so the general idea is that you have an MDP, you have a policy, and now you want to figure out what are the future expected rewards of following that policy. So what you can do is you can kind of plug in the policy into the MDP and then run it. So then you've kind of factored out the exponent here. You factored out the choices, the decisions that you have to make. So you get what is sometimes called a Markov reward process, which is a coalgebra of this type. And yeah, this is just plugging in the policy here. Now, we know these kind of coalgebras very well from coalgebra, and we know that we can do something called abstract determinization. I will explain it in some detail on the next slides, but just to give you an idea of where we're going. Given such an M, we can get this M sharp or M sigma sharp. Basically, well, it fits into this diagram. So we start with the Markov reward process. Now we can determinize it, which means that we go to the state space delta S. So now we have a coalgebra of this type. And this is of the same type that Clemens also mentioned in his talk. So we know these coalgebras also very well, namely the final coalgebra is the coalgebra of infinite streams or infinite sequences of real numbers. So we get this unique map into the streams over the reals. And so with every state S, we can travel this way, and the composition is denoted by, well, it's called the trace semantics of this guy. And basically, it sends the state S to what are the sequence of expected rewards at each time step when you follow your policy and starting from that state S. Okay. So if you are not familiar with this construction, and because I will need some of the technical details later, I will just briefly go into some technical preliminaries now. So it's based on the theory of distributive laws. And, well, a distributive law of a monad or a functor is a natural transformation of this type, which respects the monad laws. So they basically have to, these equations here have to hold. Now, if you have such a lambda, then some of the things we will use is that you obtain also liftings of the involved functor. So you get a lifting of your functor f, so of the coalgebra type functor, to the category of Eilenberg-Moore algebras for the monad, so the category of algebras of the monad. In the case of the distribution monad, it's the category of convex sets or convex algebras. And it works like this, basically by composing with the lambda, I mean, applying f and composing with lambda. And also dually, you get a lifting of the monad to the category of coalgebras. And it works, well, dually. Okay, so these will come back later. Sorry? And that lifting is a monad? No. No. Oh, sorry. Yes, it is also monad. Yes, but we don't use it. Yeah. Okay, and also from such a lambda, we get this abstract determinization construction, which sends an ft coalgebra to an f lambda coalgebra. Now the underlying is this is also an f coalgebra because you can just forget that you are actually in the category of Eilenberg-Moore algebras. So you can see it as a map that sends an ft coalgebra to an f coalgebra, if you like, and it basically works in this way. Okay, so now we can do this for the Markov reward processes. Namely, well, there are different ways you can view it, but basically we have a distributive law of the distribution monad over the stream functor h, because we have an Eilenberg-Moore algebra on the output set, basically on the set of reals, and this Eilenberg-Moore algebra is just the expected value map, which I denote by E. Oh yeah, actually I thought I had that on the slide already, but must have disappeared. And the distributive law just looks like this. You just project first, and then you have, each of your components, you apply the expected value in this component. And there you have it. You distributed the delta over the R, so to speak. So if we now instantiate this determinization construction for this monad and for these functions, then this is what we get. So we should kind of do a sanity check that we actually do get the expected rewards. And yes, you can see that you do. So the determinization is then something that takes a mixed state as input. And what you get as output is the expected reward with respect to your mixed state. And the transition map that sends a state S to the distribution that you get by applying the transition structure you get from your policy to your current state. Okay. So here we have the picture again that I mentioned. So in order to speak about the long-term value of a policy, basically what you want to do is you want to evaluate this infinite sequence of reals somehow. And there are different ways of doing that. And as we've already heard today, the discounted sums criterion is a particular one, but there are also these limiting criteria where you look at limiting averages and so on. But I will indeed focus on the discounted sums in my talk because they have nice mathematical properties, partly. We fixed some discount factor, which is just a real valued number between 0 and 1, so strictly smaller than 1, because we need this kind of contractive property. And then the long-term value of a policy sigma, according to this criterion, is then a function from states to reals, right? The state to its long-term expected value, and it's basically this infinite sum here. And it converts, so this is an infinite sum, so does it converge? Yes, it does, because we've assumed that the state space is finite, so it means that the rewards are bounded. Okay. Am I going too fast, or is it okay? Okay. Sorry?
I guess it's obvious, but even if you have a number of states as infinite, you're still just going to get It's okay. Okay. So in general, you can, of course, have an infinite state space, but if you assume that your reward map is bounded, then you still have convergence of the sum. But since we assume finiteness, because it's just much easier for many purposes. Okay, so once we know how to assign a long-term value function to policies, we can also lift that to an order on policies. So we just say a policy sigma is better than a policy tau if their value functions pointwise, if the value function of sigma pointwise is better than the value function of tau. And so it's also clear what should be an optimal policy now. Namely, it's just a policy that's better than all other ones. Okay, so the long-term value functions were parametric in a policy, right? But we're also interested in what would be the best that one could possibly obtain, and that's what's called the optimal value function. So this is basically a value function that maximizes over all of the long-term value functions you might get from a policy. And there's, I didn't mention this already, but the theory of NVPs is very well developed. There's a lot of results known for many different criteria for all these variations that I talked about. So here are some of the ones that apply to the setting that we are in. So some of these do not hold for some of the other limiting criteria, for instance. But what we do have is that if you have an optimal policy, then indeed the value function is also equal to the optimal value function. And we can always find an optimal policy. There is always an optimal policy. And now it should also be clear that these optimal policies need not be unique. The value function is always unique, but there could be different ways of obtaining the value function. And also, we restricted to these very simple policies that it's just a map from states to actions. And you might wonder, can we do better? Like for games, we know that sometimes you need to have mixed strategies in order to obtain equilibrium. But for these MDPs, it's known that the optimal value function can be obtained by a policy that is deterministic and stationary, so also memoryless. So when we look for the optimal policies in this space, we are sure to find it. Okay, so this was, a brief introduction to the basic theory of MDPs. So let me go into the first part. So like I mentioned, we would like to get this long-term value function in a more, let's say, categorical manner. And for that, we start from the observation that the discounted sums, as we mentioned before, they have a kind of recursive structure to them. So this value function basically satisfies the following equation, which is a recursive equation. You have here the V sigma again. And you can think of this as a linear system of equations. So if you think of the value function, because it's a map from S to R, S is a finite set, so you can just think of it as a vector in R to the power S, or Rn, if n is the cardinality of S. Then this is just a linear system of equations that you can write in this way. So here's the gamma. This is the T sigma viewed as a matrix, S by S matrix, and, well, here a vector again. And such a linear system, well, you can solve it. So another way of looking at this is also that the V sigma arises as a fixed point of this linear operator. And, well, in order to get to the category theoretical story, then, well, the basic observation is that we can also express this equation in a coalgebra to algebra, as a coalgebra to algebra morphism. So it means that the V sigma makes this diagram here commute. And, well, this was the expected value function, as I mentioned before. And down here, we have what we call the discounted summation algebra. So what it does, it just takes two reals, and it computes the discounted sum of the two, so x plus gamma times y. OK, so we have a coalgebra to algebra morphism. And what we would like to have some mechanism to evaluate or to get long-term values in general. So it's kind of the next obvious question is, well, is this algebra we have at the bottom, is it a co-recursive algebra, which means that it has this universal property that whichever Markov reward process you present, it will evaluate it. It will give you this long-term value map. So, well, is this the case? Yeah, this is the definition of being a co-recursive algebra. Now, by a result by Capretta, Oosterloo, and Vene, this guy is a co-recursive algebra for this composed function, if and only if the summation algebra on its own is a co-recursive algebra for the stream functor. I'll come back. I'll come back to this result later. So now, okay, so we've reduced our question to a simpler one here. So is the summation algebra then a co-recursive algebra, which means that, well, we would have this property. Well, think of this coalgebra. So it means that we would have to be able to give it any coalgebra, right? So if you now take a coalgebra that looks like this, so it has, an infinite number of states, and this is just a sequence of rewards or output values at every state, then having a solution F dagger means that, well, this equation is satisfied for all n. Okay, do we have a solution? Yes, we have too many. We have infinitely many solutions to this equation, namely when gamma is greater than 0. Namely, you can just take any value for F dagger at x0, and then the next one is defined from that, right? So if you know what this is, then you subtract an and you divide by gamma if gamma is not 0, and then you have your next one, and you keep going. Okay, so, well, the summation algebra is not co-recursive when gamma is greater than 0. But you can also see that if this sequence of ANs is bounded, then there is actually a unique bounded solution. So there are still infinitely many unbounded ones, but there will always be one unique bounded solution. So if the sequence is not bounded, you still have infinitely many solutions. But if the sequence is bounded, you have infinitely many solutions, but a unique bounded one. Okay? So this is the important aspect. So in order to get this kind of universal property that we're looking for, we need to incorporate this boundedness information in our categorical setup. So we do that by introducing something we call a B category. So it consists of a category together with a subclass of morphisms that you should think of them as the bounded morphisms. But all we require of them is that they satisfy the following property, namely whenever you take such a bounded morphism and you precompose it with any other morphism, then you are still bounded. And if you think, if F really was a real, actual bounded morphism, you see that this is an obvious characteristic that bounded morphisms have. And I will learn at CMCS that these guys are actually known already as sieves. So I don't know if maybe some of you can see some interesting connections to the theory of sieves. So I would be very interested in hearing about that. Now, of course, the main example we have in mind is the category of metric spaces and the actual bounded functions. And here we take as metric spaces, but we take actually all maps between metric spaces. So it would seem more natural to take, let's say, non-expanding maps or Lipschitz maps or something. But actually, all the information that we need is encoded in this B. And that's why we do not need to complicate our lives by restricting the morphisms between the metric spaces. OK, so the notion of co-recursive algebra that we need is, we call it a B co-recursive algebra. So it's basically restricting to B in the right places. So it basically says that whenever you have an F co-algebra that is also in B, then you have a unique solution map that is also in B. OK, so that's where we're headed. Of course, we're not quite there yet. We're setting things up now to get the long-term value. So this is basically the roadmap to getting there. So it's clear that if we can show that this algebra that we saw earlier, if it's a BCA, then we get the long-term value map from the universal property. And for that, we develop a bit more theory of these B categories. So we define some concepts of functors and natural transformations and so on. And we also prove a B version of this Caprese-Helle result that I mentioned earlier. And then finally, because this result basically allows you to take a BCA for the simple functor and turn it into a BCA for the, let's say, composed functor here, functor with a monad under certain conditions, then we also need to show that we have a BCA for the simpler functor, namely that this alpha gamma itself is a BCA. And of course, we should check that all the conditions for applying this theorem applies. OK, so let's see how we briefly do this. So some of the concepts that we've developed, you could say this is work in progress. This is basically what we need. You can ask, is that natural or what? But it's what makes things work for us. So we need the notion of preserving B, so arrows that preserve B. So it's basically what you would think. So if you take something in B and you apply your F to it, then you are still in B. And now we define a functor to be a B functor if you take something in B, so an F in B, then F of F preserves B, so B prime, because you are now on the other side. So you might have expected this condition instead, right? That the functors map bounded maps to bounded maps. But this is, it's a stronger condition. And we don't always need this. And we don't always have it either. So that's also partly why we need to introduce this, take this as the more basic notion. OK, so we also need natural transformations. We want all these distributive laws, et cetera, to also live in this B environment. And again, what we need is basically a natural transformation between just ordinary functors, so not necessarily B functors. Well, this is a B natural transformation if all the components preserve the B. All right. So now we should check that the concrete setting of the MDPs also fits into all of this. And what we find is, first of all, we need to lift our functors to the category of metric spaces. And, there are actually different ways of doing it. But, this one works for us. So, this is a product here. So on the product of metric spaces, we take the maximum metric. And when we apply the monad, the distribution monad to a metric space, well, we get a new state space consisting of distributions, and we take as the metric on distributions the Kantorovich lifting of the underlying metric. So again, there are, I think, 10 different ways of defining a metric on distributions, but this is also one of the, let's say, better known ones, and it also has nice mathematical properties. Okay, so once we've set this up, then we can look at what. Sorry? Yes, I can. It's a bit involved. Shall I do it after? Yeah, I mean, I don't know if the details are really important. Right, yeah, so I'm not going to do any proofs of any of these statements. But what you can show is then that when we consider the stream functor and the distribution monad as functors on metric spaces, then the stream functor is a B functor, but it's not a strong B functor. The distribution monad is a strong B functor. And the, let's say, important natural transformations, so this is the distributive law, and the monad structure are also B natural transformations with respect to this structure. And here, I mean, this is where we had to kind of make a choice. So for the product, you could have also taken the sum metric. I mean, there are different ways, and then we say, oh, now we don't get, well, one of them, I forget now which one was no longer a B natural transformation, which we need. So, yeah, there's some ad hoc aspect to it, I will admit that, but this is what works for us. And what you can also show, we want to do this determinization construct, right? So what we also have is that if you take a Markov reward process that lives in B, then also the determinization lives in B. So this will also follow from all of these earlier results. Okay. So the next step was to get this B version of the Capretta et al. Result. And I'm just going to state the theorem. We need to have a lot of, quite a few assumptions. But this is basically how it goes. So, I mean, we have to have a B category. So this is a general version, right? So we have to have a B category. We have to have these ingredients, the functors. So we have to have a functor on C. We have to have a monad on C and a distributive law of the monad over the functor. And we need that T is a strong B functor and that this distributive law and this natural transformation are B natural. So this is basically needed to ensure that determinization is also in B. Okay, so what we get from this is that if we have an algebra for the lifted functor, so an algebra in the category of Einberg-Moore algebras here, so with the underlying convex structure given by this theta, in such a way that the underlying F algebra is a BCA for F, and the convex structure preserves B. Then we get a BCA for the composed functor by precomposing with this F theta. So if you think back, the algebra that I wanted to show as a BCA was actually of this shape. And we also get some relationships between let's say, the solutions you get from the BCA for F and the solutions you get for the BCA for FT. Yeah, I mean, I'm not really going to use any of these now in what I'm going to show, but you will need this in order to prove where we want to go. Okay, so the proof is, okay, so I should say that Capretta et al., they proved their theorem actually in dual form. So they proved it about comonads and so on. But I mean, the proof is, I mean, it's basically the same in terms of that aspect. But what we've added is, of course, all this B information. So now you need to make sure that indeed all this B stuff is preserved wherever you need it. And well, you can do that. So the details are in our paper. I'm not going to go into all the technical details here. Okay, so steps 3 and 4 were to actually obtain these BCAs that we want to transform using the theorem. So the first one is to show that this summation algebra is actually a BCA. And there, yeah, you would actually need the definition of the Kantorovich lifting. I'm not going to, yeah, I'm not going to show it. I can do it if you are interested and if I have time. But basically, the important point to make is that there's no free lunch here. In order to show that this guy is a BCA, we actually really need to apply the Banach fixed point theorem. And one of the motivations we had was to kind of get away from the classical kind of analytic theory and replace it by categorical reasoning. But this is a place where we, in order to get off the ground, we need to resort to the Banach fixed point theorem. OK, and the next step was, we want to apply our theorem, so we need to check some of the assumptions. Namely, we needed to have this thing we start with to be an algebra in the category of Eilenberg-Moore algebras, right? And this is basically this property here. And you can check that, that's what it means, that this diagram commutes, and that indeed the diagram commutes. And furthermore, you can check that the expected value also preserves bounded maps. This is more or less immediate. OK, yeah, so actually, yeah, once we've done all of these steps, then as I showed in my overview, I think it's clear that then we have this BCA that will give us the long-term value for our policy. Now you can try to do the same thing for the optimal value function, right? So we have this diagram. We would like that to be a BCA diagram. And in fact, it is. You can show that this guy is a BCA for this functor. But we cannot show it by applying our theorem 2, unfortunately. So we really have to show it from scratch, again invoking the classical theory, which is a bit annoying. But we tried many different ways of to make it work. But the problem is that this max map, so this is a map of type r to the power a to r, right? So you have a collection of real values, and you choose the max one. This map is not affine. It's not a morphism in the category of Eilenberg-Moore algebras. So this is the technical showstopper for applying this theorem. But as I said, you can't just show directly that this guy is a BCA and that you therefore have the optimal value map given by a universal property. OK, I think this was the end of my first part. Are there any questions so far before I continue with the second part? I'm not sure I'm going to use all of the time, actually. Did I start it too? Oh, OK, maybe. Oh. OK, yeah. But, yeah. OK. Then I will move on to the second part, which you may find more interesting. It's a bit more, we cash out a bit more on what we've been doing. So it's about giving a co-inductive proof of policy improvement. So first, I'm going to introduce a bit of notation. But I gave the talk at Strathclyde. I got confused because I had changed notation. And now I thought, OK, let's just stick to what we do in the paper. Then it's clean. And it's also nice. I mean, it makes it, let's say, more compact to read. So given a policy and a distribution, then we can define this map. Well, given a policy, we can define this map, little l sigma. And it has type, I should have written that. It has type from delta S to R. OK, so what it does is it takes the value function associated with the policy, and it computes the expected value with respect to the distribution that you feed to it. So concretely, this is the sum that it evaluates. OK. Now the policy iteration algorithm works as follows. So it's an iterative algorithm. So you initialize to some policy, can be any policy. Now you can compute this value function, for example, by solving this system of linear equations. And then you define a next policy in the following way. You take the action that maximizes the expected long-term value for the current policy with respect, to the transition, kind of the distribution you get from choosing this A. So the A that maximizes this expression here. And then you check, is the next one the same as what I already had? If so, then you stop, and otherwise you iterate. OK, so first of all, it's clear that this will terminate because I assume that A and S were finite, so A to the power S, the space of policies, is also finite. And the correctness will follow if I can show that actually what I'm doing here is actually an improvement step, right? That the next policy is actually better than the one I had, or at least as good. So that's where we are headed. so before I state the thing that we want to prove, then, yeah, it's useful to think of it in this way. So the way we define this next policy implies that for all s, we have this inequality, right? Because this sigma k plus 1 takes an action that maximizes this expression. So choosing here, using the sigma k plus 1, is you should get something that is at least as big as what you would get with a sigma k. Okay, so now you can, of course, see this as an equation, a pointwise equation of functions. So you have this equation. So we realize that what we need to show is actually the following. And, well, we realize, I should say, Howard already in 1965 realized that this is what you have to show. Of course, he didn't write it in this form, but essentially the same idea. So for all policies, yeah, if you have this inequality, then you can deduce that the tau is also at least as good as the sigma. So the tau is the improvement policy, right? Okay, so we do this using this new principle that we introduced called contraction coinduction. And it's a proof principle that incorporates both metric structure and order structure. So the setting we're in is basically that of a metric space that also has some order on it. So for the real numbers as well, the one that you would expect. But what we need is the notion of an ordered metric space or ordered complete metric space if the underlying metric space is complete. So it consists of a metric space together with a partial order, but in such a way that upsets and downsets are closed in the metric topology. We will need that. And of course, the main example that we are going to apply it to is the space of all bounded functions from some set into R. Okay, so the contraction coinduction principle can be stated as a theorem. So if you have a non-empty ordered complete metric space, and you have a function on that space which is both contractive and order preserving, then, well, first of all, by the Banach fixed point theorem, you know that there's a unique fixed point. But now this contraction coinduction principle tells you that also this unique fixed point is also a least prefixed point and a greatest post-fixed point. So it gives you an induction principle as well as a co-induction principle. And yeah, so you can prove this. We do this. You can prove it directly. Just I can do it on the board if you're interested. Just using the order preservation and the contractiveness and limits and so on. But you can also prove it using Cosen's metric co-induction principle in a few steps. So you could also say that actually we do not even need to have a partial order. You can start generalizing and saying, well, we don't actually really need this or that. But then what you will eventually come to is the metric co-induction principle, so to speak. So first we said, yeah, but we should be as general as possible. And then we realized, no, actually, we don't want to be as general as possible. We want a proof principle that is really useful for the particular setting that we are in. And this is just a very handy, well, this formulation is the useful form of metric co-induction, you could say, for showing these inequalities of value functions, etc. And I also want to mention that already back in the 60s, Donato has a paper also on MDPs, and he also shows various results involving order. So it's not formulated in this way, but he certainly already had the inkling that the order structure and metric structure should interact. Okay, so now we can prove the policy improvement lemma in a few steps, basically. So this is what we want to show. So of course, we're going to apply the contraction coinduction principle. And what are we going to apply to? Which f are we going to apply to? Well, we're going to apply it to this operator that we saw before, the operator that gives us the value function as its fixed point. So this linear operator here. So what do we have? Well, we start with our assumption. Now, well, you can easily see that if I multiply with gamma and add the rewards on both sides, then of course, the equation still holds. And I see, well, this is exactly just the operator. So what this says is that the psi for tau in the value for sigma is greater or equal to the psi for sigma in the value for sigma. But this was the fixed point here. The value for sigma is the fixed point. So what we've shown is that the v sigma is the post-fixed point of the operator for tau. So by contraction coinduction, the value function for tau must be greater or equal to the value function for sigma. And that's what we wanted to show. All right. that brings me to the end of my talk. So yeah, so we've seen now how to get these value functions from this notion of B co-recursive algebra that we introduced, and I've shown you how you can use co-induction to give a proof of the policy improvement lemma theorem. What we've done is, we haven't shown anything new, of course, about MDPs, but what we've done by using contraction co-induction in particular is that we've kind of encapsulated the reasoning with limits and continuity into this more high-level algebraic proof principle. But as I mentioned already, in order to get off the ground and actually prove or reprove the theorems, then we still need to resort to the Banach fixed point theorem. Okay, so there's of course lots of future work to be done. So yeah, one is of course that we would like to go to stochastic games, and we've already looked at this. And I'm pretty sure it works, but I want to go through all the details before I really would present it. But what we can prove for stochastic games is the generalization of the existence and uniqueness of these value functions is the existence of Nash equilibria. And basically what you can do here is that you can still use the contraction co-induction principle to show that a profile is actually a Nash equilibrium, so showing that it satisfies an optimality equation. But since you have several players, you need a more refined fixed point theorem, namely Kakutani's fixed point theorem. But you can say that the proof of the existence of Nash equilibria can be stated as Kakutani plus contraction co-induction. And of course, there are many other types of equilibria out there. It would be interesting if we could say something about them in a co-algebraic or categorical way. And of course, we want to also make connections to all the other exciting work that is happening right now. And another line of research that Clemens in particular is engaged in is learning. And knowing that MDPs have, are basically models of reinforcement learning. And I don't know if Brendan's going to talk about that tomorrow or reinforcement learning. Yeah, so I'm looking at. Yeah, so yeah, so it would be interesting to make connections to that part too. All right, thanks.